Hi everyone, and welcome to this lecture on principles of induction. So this one's kind of going to tie in with the previous lecture, magnetism, and it's going to lead us to the next one, which is going to look more at inductors themselves. So we spoke about resistors, that's a component, capacitors, that's another component, and inductor is another component. And unfortunately, or fortunately, depending on how you like it, it's the hardest one of all these three to understand. There's quite a few things to think about with them. Okay, so just let me show you a few things. So I've got some text here that we're going to have a bit of a read through. Some laws, Lenz's law we're going to have a look at, some things that Michael Faraday found. I've also drawn up a few different circuits here, just showing you different examples of what would happen with these magnets and these coils of wire to see what actually takes place. Now to help us along with this, I've come up with a little magnet that I can move around here, and I'm showing the lines of flux. Normally they're invisible, but those purple lines indicate the lines of flux. So if you remember from the previous lecture, the magnetic lines of force, or the lines of flux, are those lines that we can't see, but we can actually feel the effects of them. Now the stronger the magnet is, the more of those lines that we would actually have. I've then got this over here, so you recall from the last lecture I had this one here, which is a coil of wire going around a screw in this case, and as we connected a power supply to there, that would give us a complete circuit. Current would flow through the coil of wire. Now that current flows through the coil of wire, we get a magnetic field built up around the coil. So apply a voltage, you get current. By getting current, you produce a magnetic field. But notice this one's a little bit different. So I've got a resistor here. I don't have a power supply connected there. I'm actually doing the opposite thing. I'm actually going to be using this as a bit of a power supply, connecting a resistor to there. And then this is going to provide the voltage to get electrons to go through the circuit, and we'll see how that works soon. So I can move this around. I've got this arrow here which is going to show the direction that I'll be moving this in. I've got a south and a north pole to show, because this is going to turn out to be an electromagnet, so we're going to get a south and north showing up somewhere there. This is going to be a power supply because we're going to induce a voltage into it, so we get a negative and positive showing up somewhere. And then we're going to have some kind of current flow in some direction, and that's what these ones are going to represent. And this one just does the opposite. Okay, so it's going to be a pretty interesting ride as we go through this one, so let's see how we go. Now, the first thing I want to have a look at is, here's a magnet. We've got those magnetic lines of flux going around it, which is like the field around the magnet. If I was to get that magnet and start to move it across like this, now just pay attention to, we've got the south pole coming in first, but pay attention to these purple lines of flux, and then the top pieces of the coil of wire. As I move the magnet in, can you notice what's happening with those lines of flux? What are they doing to those wires up the top there? Well, they're actually cutting through it. So we're actually cutting through those wires with our lines of flux. Now remember, these lines of flux would actually be going everywhere, like a three-dimensional pattern all out of here. So as we move the magnet through, it's actually cutting through every single part of those wires, not just the top or bottom parts of it. So an interesting thing happens when you actually get lines of flux, or the force field around the magnet actually cutting through wires. You actually induce a voltage into it. So this, in fact, this is probably a better example here. Here's a coil of wire going around just some plastic tubing. As you can see, it's hollow. If I get my magnet and I was to move it in and out of there like that, as I'm moving it in and out, I'm cutting through those wires with my magnetic lines of flux. I'm inducing a voltage into it. So if I was to connect a voltmeter across here instead of a resistor, you would actually get some voltage showing up on the voltmeter. Now the thing is, this only happens, you only get a voltage induced into it if you're moving. So if I was to move that to there and then stop, there is no movement anymore. Therefore, there's no actual cutting of those wires with the magnetic lines of flux. If there's no cutting, there's no voltage induced at all. I like to think about it with, say, a knife. So I know this is not a knife, it's a pen, but if I get this and, ooh, hang on, here's a knife or a blade. So if I get this blade here like this, and for some reason I want to cut this pen in half, I won't because I need to use this for the tutorials. If I was to get this and I get the knife and I just put it on top there and it's stationary, it's not moving, is that going to cut it? Is this going to get cut in half? It's not. What needs to happen is I need to start getting some movement going on in order to start cutting through this thing in order for something to happen. Well, that's exactly the same when we're dealing with our magnets right here. I can hold the magnet in there, but if I don't actually start moving it, I'm not actually cutting through any of those wires, so I'm not going to get a voltage. So there needs to be movement for this to occur. Okay, so I move it in and out like that. If I just kept doing that and I had a voltmeter connected, the voltmeter would keep going up and down with the voltage as I moved it in and out. Now, let's have a look at over here some things I've written up. So the green text first. If you move a magnet through a coil of wire, or vice versa, so either move this in and out of that, or move this on the outside of that, you will generate a voltage, or probably a better word is induce a voltage into those wires, otherwise known as electromotive force, EMF. Now that we've got a voltage, we know what happens when you connect a voltage to a circuit. You get current flow through the circuit. So this voltage produces current flow. And from the previous lecture, we learned that if you have current flow through some wires, you get a magnetic field built up around those wires. So us moving this through here cuts through some wires with the magnetic lines of flux. That induces a voltage into those wires. Now that we have a voltage in those wires, we get current flow through the wires. And of course, every time there's current flow going through wires, you get a magnetic field built up around the wires. Now something interesting happens with that. And this is where Lenz's law comes into it. So you could look this up on Wikipedia. I'm paraphrasing just a little bit. Lenz's law tells us that the polarity of the generated magnetic field around the coil of wire, right here, is going to be such a polarity, so the north and south pole will show up, such that it's going to oppose what we're trying to do. So if I'm pushing the south pole in here like that, as I'm moving it in there, it's cutting through the wires. We're generating an EMF or inducing an EMF into this. We get current flow as long as I've got an external circuit connected with my wires. We'll have current flow. That current flow produces a magnetic field, and that magnetic field will actually be opposing this one. So if I'm trying to push the south pole in, the south pole for this electromagnet will show up over near the south pole of this one, trying to push it back out. So let's have a look at that here. We push the south in, so let's grab this. This is the way that I'm going to be pushing it in. Notice the south pole is coming in first, and this is moving in through here. It cuts through those wires. It induces an EMF, or a voltage, into those wires. That gives us current flow, and then that current flow results in a magnetic field that's opposing, this other one. There we go, coming in there. So therefore a south pole will show up over here, because if you put a south and a south together, they repel. It's trying to push it out. Therefore the north pole must come up over the other side. Now let's think of, well, which way will the current actually be flowing? Well, now that we've done this, we can work out the direction of current flow. So let's use Fleming's left-hand grasp rule here. Thumb pointing in the direction of the north pole. We wrap our fingers around. As you can see, my fingers are going down around the back. So the current is going up at the front, down at the back. So this is what's going on with the current. So the electrons are traveling up through here, down the back, up at the front, down at the back, and so forth. Because we've got an external circuit, those electrons will flow through the external circuit. Therefore, we must have a negative over this side, positive over this side. So let's just come over here so I can draw a little something. This is the same circuit that we were just doing. Effectively, this here looks like a power supply. We've got a positive over this side and negative over this side. And there's our resistor. That's all we're really doing. We're just making a power supply by moving this magnet through the coil of wire. There's the negative, there's the positive. Why do we have negative there, positive there? Well, that's because follow through the external circuit, the electrons are going this way. If the electrons are going from right to left through the circuit, and the electrons come from the negative side of the power supply, this side must be the negative while this is the positive. Let's get rid of all that. So that's that example. You move the magnet with the south pole coming in first. You will cut through the lines, the wires with the lines of flux. You will induce a voltage, which means you will get current flow. Now that you have current flow, you will get a magnetic field built up around the coil, just as we looked at in the last lecture. Lenz's law tells us, well, the polarity, like the north and south oops, I should be doing this, the north and south of this electromagnet is going to be such that it's trying to oppose that magnet of whatever it's trying to do. If the magnet's trying to come in, this electromagnet is going to try and push it out. If we started with the magnet inside and we're trying to pull it out, the electromagnet's going to try and pull it back in. It doesn't like change. It's always trying to bring it back to where it was. So that's how we worked out that the South Pole shows up here, and of course the North Pole would have to be the other end. Then we can work out the current flow by using our left-hand grasp rule, thumb in the direction of the North Pole, wrap your fingers around, and we worked out that it's going up at the front, down at the back, and then through the resistor here like that. So therefore we have negative, positive. Wow, that was a bit of a mouthful. Let's start with this inside. Let's rotate this around to show that we're going to go in the opposite direction. And let's get rid of all these. What is that going to do with our circuit? Okay, same sort of thing. So we grab onto this. We're moving it. North pole coming out first, south pole coming out last. So we're going from right to left. That is going to cut through the wires with the magnetic lines of flux, which is going to induce a voltage, which is going to produce current flow in the circuit, and that current flow produces a magnetic field of its own in that coil. What's the polarity? Well, let's go back to Lenz's law. If I could click properly. So Lenz's law tells us that the polarity of the magnetic field is going to be such that it's going to be opposing or trying to prevent whatever that permanent magnet is trying to do. So this permanent magnet's trying to move that way. This is going to build up a magnetic field to oppose that. So a north pole is now going to show up over here, because if you put a north to a south, what are you trying to do? Well, you're trying to pull the magnet back in. We don't want it to go out. It's always trying to do the opposite of whatever the magnet is trying to do. Which direction is the current flow going in? Well, let's get our left hand, thumb pointing to the north, wrap our fingers around. It's going up at the back and down at the front. So it'd be this way, opposite to what we had before. So what about the polarity of the power supply? Well, the electrons are going down from left to right. They must be coming from the negative. So this coil of wire is giving us a voltage with a negative polarity over here on the left and positive on the right. It's just like we've created a battery. In fact, you may have those, or you may have seen those torches. With the torches, you know how you wind it? You wind it around, 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 and the torch actually charges up, or it turns on when you wind it. This is the kind of thing you're doing. As you wind it, you're actually spinning a magnet through a coil of wire. As you spin it through, it's cutting through the wires in there with the lines of flux, and you're generating a voltage. So, and then this here would be replaced with your lights. So you're actually spinning it, and it turns on the light. Okay, so it's going to try and pull it back in. Well, I guess that's all to say just for the moment for that, but let's have a look at what Michael Faraday found. So Michael Faraday found a number of factors that determine how much voltage gets induced in the coil. So sometimes we'll get a small voltage, sometimes we'll get a really big voltage. So how does that work? Well, the first one is the speed that you're moving. Is it the speed? Yes, it is. So if we were to move this really slow. So think about it with a bike. If you pedal really slow, how fast is the bike going to go? Well, it's going to go really slow. With this one, if you move it really slow, you're cutting those wires really slow, so the amount of voltage you get is really small. But if you were to move it really fast like this, in and out, you're going to be cutting through a whole heap of wires really quickly. You get a bigger voltage. So the speed certainly plays a big part. The number of turns of wire in the coil. So this here, there's only, 4 turns of wire, so as we move this through, we're going to be getting very small voltage. But if we were to increase the number of coils of wire there to 100 or 1,000, you're going to be getting a much bigger voltage for the same magnet going through there. So this one here only has a few turns of wire, yet this one here has hundreds of turns, so this one would get the bigger voltage, because there's more wires to actually induce a voltage into. The strength of the magnetic field. So if we get a pretty weak magnet and we move it in there, you're not going to get a very big voltage, but if you get a really strong, powerful magnet and put it through the same coil, you're going to get a much bigger voltage induced into it. Now the last one to have a look at is the angle that the wires are being cut. So this one here is a bit trickier to understand than the other ones, but if we were to get, say, a few pieces of celery, let's grab this one, And let's get a few more of them, like that. And then we would come along with our knife. The best way to cut this, or the most efficient way to cut, would be straight through like that. Because in order to cut through every single one of them, you have to go the shortest distance to do that. So the quickest time would be to go straight down. You could also cut at this angle, but notice to cut through every single one of them, we have to go a longer distance. It's going to take more time because the angle that we're cutting at is not that 90-degree angle. What would be the worst angle? Well, the worst angle would be if you were to go straight across like this. That wasn't a very straight line. Straight across like that. So what I'm trying to show here is, is that we actually haven't cut anything at all. So if we were to go straight across like that, see how we're completely missing everything. We're not actually cutting any of those celery sticks in this case. It's the same thing with a magnetic field. So if you were to get a magnet like this and go in and out like that, you've got lots of magnetic lines of flux that would be cutting through the wires, but if you were to rotate it this way and put it in and out, you're actually going parallel to those lines of flux and you're not cutting through any of them. So the more lines that you're cutting through, the more voltage you get, but if you're actually going parallel to those lines, you're not cutting any of them, so you don't get any voltage. So they're the four things that determine how big the voltage difference between these 2 points will be when you move a magnet through there. Alright, so that's... Actually, we've got just a tiny bit more time, so let's just go over this other side. If we were to move the permanent magnet in with the north pole first, so we're still going to be going in this direction, what's that going to do? Well, we push it in with this direction like that. Lenz's law tells us that as we cut through it, and we're going to get a voltage induced which produces current flow, which gives us a magnetic field. That magnetic field will be such that it opposes what's happening, which means a north pole must be showing up over this end. If a north pole shows up over that end, it makes sense because it's trying to push the magnet back out. We use our left-hand grasp rule, the thumb over to the north, fingers wrap around, the electrons would be coming up at the front, down at the back, which means it's the opposite to that one. Up at the front, down at the back. Therefore, electrons are going from the right-hand side to the left-hand side, so the power supply polarity must be this way, like that. What about if we started with that inside and then we moved it out? So let's grab that. Let's move it out this way. Notice the south pole is the one coming out first, north pole is last. So we're cutting through those wires. It gives us a voltage induced into the coil of wire. With a voltage induced into it, we get current flow through it. That current flow produces a magnetic field. Lenz's law says, well, this magnetic field is going to be such that it's trying to oppose what that magnet is trying to do. Therefore, a south pole will show up over this end. It's trying to pull that north pole back in. Use our left-hand grasp rule, thumb over to the north, wrap our fingers around this way. The current is coming down at the front, up at the back. Therefore, the electrons must be going from left to right through the load, so there's our power supply polarity. Again, if we stop the magnet, if it's not moving anymore, we get 0 volts because there's no induced voltage if there's no movement. Alright, so go back over, maybe look at this lecture again, but go through this PDF that I've got there. There's the 4 different examples I've gone through right there. Hopefully they'll help you out, and then see how you go with the exam, and then we'll get on to inductors next, so that'll be a lot of fun. Thanks for watching, guys.